thank you very much for having me along virtually today. I'm very sorry I couldn't make it in person. I had some teaching that I couldn't rearrange, but I'm really happy to contribute to hopefully what will be discussion today around thinking about how we teach practical work, how we teach in laboratory environments. And what I wanted to share with you were some ideas I've been thinking about regarding how we formalize our conception about what laboratory teaching is. And what I mean by this is we have students completing practical work. So I have students and they're chemistry students, so they'll be completing chemistry practical work. Across the sciences, across the audience today, there'll be people with from different disciplines. And we all consider practical work to be of value. We consider practical work has a particular role in our curriculum. But certainly in chemistry, there is a sense that there are some issues regarding the teaching of practical work. So a very famous review in chemistry is that by Hofstein and Lanetta, and they sort of impart this sense of frustration and disappointment regarding teaching in laboratories at school level as well as university level, that we haven't really grasped the nettle about how we think about teaching in laboratories, how we can maximize the educational benefit of laboratory work. Against that argument, or that sort of position, is, for example, the bottom left here, Kirshner's article, a very good essay to really make you think about practical work. And this really sort of sets the scene for a lot of what we would call innovations, and really thinking about the role of science and teaching science, teaching practical science. So there are kind of two sort of literature theoretical bases for thinking about the issues regarding laboratory work and the problems regarding teaching in laboratories. On the other side are two recent publications on the Towns Research Group in America. And I think these are very important publications because they really give a sense of what the student is saying about practical work. And I'm afraid to say that the news isn't good. The students essentially seem to report that regardless of the level they are at, practical work, effectively the task of completing practical work from a student point of view is to get the job done as quickly as possible, to achieve what is needed in the laboratory so that they can go and write their report, because it is a report that will be assessed. So I think there are issues around practical work, both from a theoretical point of view, from an observational point of view, that show that we need to really think about again how we are teaching practical work, how it fits into our curriculum. So I've been thinking a lot about why are we having such issues with practical work, and trying to come up with a framework, or at least conceive practical work within an existing framework, and see if this can address some of the issues we're having. Now, of course, we're not monsters. We, as educators, me as an educator, of course, try to improve, and we continually change and adapt and try new things and refocus our thinking about practical work so as to improve things. But in the main, I feel a lot of these initiatives are what I would call outcomes focused. So we try and make the laboratory better by considering it from the context of, well, what outcomes will be a result of the changes that we make. So there are various examples of different types of outcomes. From laboratory work, Reed and Shaw published a nice list where they define 4 general types, those being skills relating to the subject, practical skills, in other words, the process of completing experimental work, scientific skills, in other words, learning about the nature of science, how you tackle a scientific problem, and what we would call transferable or generic skills. I think these are essentially things like learning to work in groups, problem solving, that kind of thing that we're familiar with. And even though these are well-intentioned, and I, as I say, I've done them myself, the issue perhaps with these is that they are considering the output of practical work rather than considering the framework upon which practical work should be considered. In other words, they're trying to maximize the effect of practical work rather than thinking about some of the causes about how we might improve practical work. So they tend to operate in a slight vacuum, these initiatives. Now, of course, we do tend to align to some kind of theoretical framework, so most science educators perhaps align with constructivism or social constructivism, where they sort of do appreciate that learning happens by iteratively learning new approaches to and new ideas and pulling them together to build up a concept. But I think my issue is that we have students, completing labs in a sequential basis. Students are going to be doing a set of labs, a set of practical work for their course, and the leap or the link between the sort of overarching framework where we might position ourselves in a social constructivist framework with the actual day-to-day processes and considerations in a lab. It's very difficult really to think about the actual processes that that theoretical framework might impose on the procedures and the student completion of that lab. So I feel that overarching framework, or situating yourself as a social constructivist, probably isn't enough to give you a more manageable, useful framework for running a lab class. So all of this is building up to the idea of thinking about what our framework could be. And one of the issues, of course, about practical work, long acknowledged, so Johnston and Wham is a common reference in chemistry, is that there's so much going on for a student in the lab. There's so many things that a student has to think about. So they have to think about the theory that is associated with the lab. They have to think about what instructions are being given, both in written form and perhaps what an instructor is saying to them. They have to know what kind of techniques they'll have to use, how to use them, what kind of outputs they're going to get, what that means, what kind of records they should keep, and so on. There's lots and lots of things that the student's going to have to think about in the lab. So this makes the lab environment very difficult, because if we look at something like cognitive load theory talks about the situating the learner in a learning environment where they're exposed to information, and their ability to process that information will be defined by what's called the working memory space. And information that's presented to them will impose a load on this working memory space. Intrinsic load being the difficulty of the material itself, extraneous load being how difficult it is to extract that material. And the larger those components are, in a simplistic way, the less able or the less capacity a learner will have to integrate this new knowledge that they're gaining with a long-term memory. So if we think of something like a laboratory environment with all of this information being presented to the learner at once, it imposes a very high load. And Johnston, in his article, argues that it's no wonder that students try and sail through the lab just getting what's necessary to get the data that they have found. So he wrote that in 1982, and we're still finding that out in publications in the last 2 years. So of course, one of the things people do, one of the things I do myself, is to try and ameliorate this load a little bit. So by providing some information in advance, perhaps on the theory, perhaps on the experimental technique, we try and reduce some of the load in the lab. In other words, by introducing some information to students in advance, there's not so much new information in the lab. So here I blackened in some of the circles to indicate that perhaps some of the information we've given in advance isn't imposing a load. So a lot of consideration has been given to pre-lab activities, because pre-lab activities, of course, try and reduce the load. But for me, pre-lab activities is just one component of the lab. It's still not considering an overall framework of the lab. Cognitive load theory doesn't quite reach the idea of a framework for me, because if we think of all of these components, not only does the student need to know about all of these components in a lab situation, but crucially, they're going to need to know how they relate to each other. The student isn't going to be recording information in a vacuum in the lab. They're going to need to know what that information means, how that relates to the theory, what that information they're gathering relates to the type of technique they have to use, and so on. There's going to be lots of interconnectivity, and I've just shown first order connections here, but of course there'll be lots of connectivities in the lab between all the different things that the student is meant to know. So for me, it's not just about the information that we present to the student in advance, but it's about the complexity from a point of view of the student in relating all of this information to each other. So this then gives a sense that the lab is a complex learning environment. It's an environment where not only is it lots of information, present, a very information-rich environment, but it's one where the student must also navigate through that information, understanding how to relate the various concepts to each other. And we know this as educators, because if we think of a particular laboratory approach, so here I've shown for a chemistry lab what a typical laboratory arc might be. Students might do some work in advance, and then in the lab we ask them to make things or do things or gather data and so on. And then afterwards we ask them to interpret that in the context perhaps of what's already known, summarize it and write a report. This would be a very typical laboratory approach in chemistry. And we know that this is a complex approach because it's very difficult to give feedback on this. It's very difficult to give feedback on all the different approaches, so we tend to give feedback on just the report. We tend to assess the report and give feedback on that. But if we were to give feedback on every aspect of this, there would be an enormous amount of work involved. Because it's such a complex process, there's so many things going on, there's so many interrelationships. And indeed Sadler, in his very famous work, talked about this. He talked about the idea that feedback on complex processes is very difficult. So feedback on complex processes is very difficult, but we are then acknowledging that the process itself is complex. So this leads us then to thinking about how can we conceptualize laboratory learning. And the educational psychologist Merriam-Barrow has described what he calls a complex learning framework. And a complex learning framework is defined as having these three components. One that aims at integrating knowledge, skills, and attitudes. So again, if we think of a laboratory environment, think about what's happening in a laboratory environment. We know from many literature reports that it's about students' attitudes, how students feel and are motivated about laboratory work, plus how they're able to take what they know about whatever their topic is into the lab, and plus of course the actual completion, the actual psychomotor aspect of the lab, the skills that are necessary to complete that practical work. So complex learning, a very simple example would be, for example, driving a car. The idea of integrating how to use the clutch with the gear stick while you're steering, and looking at this idea of integrating various different skills, I think really mirrors this topic that was introduced earlier, where a student is required to simultaneously process quite a lot of information. The second thing is that these different skills are qualitatively different. There are lots of different things going on in a laboratory environment. And when you are navigating through that environment, the complex learning framework talks about coordinating those different skills. And finally, a laboratory environment is, of course, actually happening. Students are actually doing work. It's not a simulated online environment. They're not reading about it on paper. They have to transfer this knowledge, this awareness of completing skills to actual real settings. So for me, this description of a complex learning framework that these authors have written for any general complex learning environment really matches on very well to laboratory learning. And the advantage of taking a framework like this is now we can begin to use what the psychologists talk about in terms of supporting learning in that environment. So they talk about supporting learning in a complex environment as being one where we should focus on the whole tasks rather than the part tasks. In other words, a laboratory activity involves coordinating lots of different skills, being aware of different levels of knowledge and having a particular attitude. So therefore there's no point in just supporting one aspect of that. We have to help students as they manage the completion of the whole task, we have to show them how to make these interconnections. And a way of doing that, a way of thinking about that in the curriculum, is to start off with a simple case of a whole scenario and gradually make that more and more complex. So we have this kind of idea of simple to complex sequencing. The second thing is, what information do we need to give students to work in a complex environment? And this framework describes two different types of information: supportive information and procedural information. And we'll talk about this a little bit later in an example. But supportive information is essentially the kind of information a student would need to have prior to going into the laboratory, sort of general overarching conceptual information that they would need to be aware of before going into to do the experimental work. So naturally that maps on quite well with pre-laboratory activities. Whereas procedural information is information they need to know as they're completing a task, be it an experimental task, so what button to press, what knob to dial, or be it a procedural analytical task, what axis to plot, what process to do to gather the data required. So we'll look at some examples of supporting learning in a complex environment in terms of simple to complex sequencing and information, the kind of information we can provide in advance and just in time. So I'm just going to show some examples in practice, and really the aim of these is to seed discussion. I'm not going to talk too much about them. The aim is just to seed some discussion to get a sense of how you might think about complex learning environment. And the overarching thing is, in a complex learning environment, we want to try and introduce students iteratively to ever more complex scenarios. So in other words, we shouldn't just immerse them in a very complex scenario where they are not equipped to fulfill any of the tasks, so therefore they certainly won't be equipped to bring those tasks together. We want to try and immerse them in a gradually more, from a curriculum design point of view, in a ever-increasing level of complexity. And one way I've thought about this is to think about a curriculum. So in Scotland we have a 5-year curriculum. It doesn't necessarily have to be this exact model, but think about, at different stages of the curriculum, what's new? What are we bringing in new at each stage? What have we equipped students with before that stage, and how can we build on that year on year? And this gives a sense of how can we see a progression through a curriculum level. So here I'm talking about how do we build in experimental design over, in this case, a 5-year period, moving from really teaching students about experimental skills and laboratory procedures, right up to the idea of experimental design, the idea of scientific research. So each year would encapsulate some element of the last year, but build on some new component. Now this model is perhaps a little bit simplistic because of course we wouldn't just have all of year one developing experimental skills. We want to of course build in decision making, build in basic choices, basic ideas of experimental design. But this is really trying to emphasize, well, what are the core aspects at each stage? And therefore, in terms of complex learning, what new bit are we adding on? What extra challenge are we adding on to students so that they can now draw in a new aspect in this simple to complex sequencing and do something additional in their learning at each stage? So, I'm going to look at 3 different examples. The first is thinking about assessment of practical skills. So in our model at the very bottom here, you see, of course, we need a way of teaching and assessing practical skills, so I'll mention that. And if we think about our student in the laboratory, and they're going to do some technique, or they have some technique that they need to do, whatever their setting is, how do they know what to do? How do they know what they are doing is the right technique? So we've looked at the model from Sadler, who I mentioned earlier, about formative assessment. And Sadler argues that in order to consider formative assessment in a meaningful way, we should give students the capacity to monitor the quality of their own work as they're actually doing it. And this means that they need to have a concept of what the standard is that they are aiming for. They need to be able to compare what they are doing with that standard, in other words, to know whether or not they're doing a good job compared to what the standard is or not. And they need to be able to engage in action to correct what they're doing so as to match the standard. This idea of formative assessment is really, as they are doing a task, they need to be able to relate what they're doing to some sense of what it is they're supposed to be doing. So of course, for practical skills, for practical techniques, this model aligns very well. So we built a model with our first year and now second year students on experimental techniques, where students, to get that sense of what the standard is, they watch exemplar materials or read exemplar materials in advance, and then in the lab they demonstrate to each other. They demonstrate to peers, so they're getting peer review. And this is really a way that they can demonstrate a particular lab technique, and either through their peers or through the information they've been given, build in the capacity to compare what they are doing with the standard. So this idea of improving, this idea of going, oh no, I did that wrong, I want to retake that, this idea of achieving the standard. And then they submit their videos for review, and if those review videos show competency in that technique, the students are awarded a digital badge. And the purpose of the digital badge really is to empower students to say, yes, I am capable in this technique. So the digital badge would have, most importantly, the criteria, the evidence that was required, that the student had to show. This is why the video is important. The evidence that the student has to show that they are competent in a particular technique. They can share these badges in social media, or they can collect them in the virtual learning environment or whatever. The purpose is really a kind of a formal acknowledgement to students to say, yes, you can do this technique. So if we think about our complex learning framework, where the students has to draw together various constituent skills, this is really about empowering them to say, yes, I know that particular skill that I'm going to have to use in some subsequent experiment. The second example is this idea of supportive information versus procedural information. So the complex learning framework says that we can provide students with two types of information. Supportive information should be presented in advance. Procedural information is best off just in time. So how might this look in a chemistry setting or experimental setting? So on the left here is a picture of a particular vapor pressure apparatus. So this is just essentially a technique that's a little bit scary for students to do because it involves a vacuum and instructions tend to be very, dial this, do this, press this, and students tend to get lost in the sort of line-by-line instructions and not really understand what the technique is about. So the kind of information in terms of supportive information, in other words, information that we would present to students in advance, would be some general overarching information they would need to be able to understand what's happening in the lab. So this will be information about the particular chemistry involved in terms of general concepts, but also information about the overarching experimental approach. In other words, what's the general idea of this experimental approach? Because in the lab, they'll be lost in the line-by-line information. This is supporting information, is really just to give them a sense of, why is this approach feasible? What is it about this approach that makes it useful? And then in the lab, the procedural information will, of course, yes, be press this button, do this, and so on. We need to give students instruction to do these techniques for the first time. But also perhaps a common case in chemistry is students haven't done the required lecture material at the time they're doing the labs. So very often they haven't got the information to hand about what kind of data analysis they should do. So this is really procedural information. We tell them to plot this graph so they get a particular slope. This kind of information can be presented just in time or even after the lab. So this is an example where we're trying to tease out what kind of information we should present in advance and what kind of information we should present in the lab. And we've detailed this a lot in our pre-lab review that's linked at the bottom of the page. Okay, and then finally, how do we start to build a curriculum where we have simple to complex sequencing? So for example, I've showed you the sort of our 5-year model, but what does a particular stage in that model look like? So this is an example from our year 3 work, where we're really trying to build in the idea of experimental design with students. And we used to have a situation where students would do 4 prescribed experiments. We built on pre-labs that worked well, and then we gave students an investigation and kind of an inquiry lab. So the idea was that students would have built up the experience in general terms in their first 4 weeks, and then in the last 2 weeks they would do an investigation. And this is a classic example of an innovation gone wrong, because the investigation was extraordinarily difficult for students. They hadn't got the capacity to think about how they were going to approach it, to think about experimental design, to think about the actual lab techniques. This was all new to them. It was very, very overwhelming. So we were trying to think about, well, how can we start to build in investigative inquiry skills? So we changed the model from the original, the top line, to the bottom line, which we call unfinished recipes. And this is essentially where we have a lab class, as usual, a prescribed lab, where students learn about techniques, understand the kind of data they have to acquire, and then rather than go on to another new lab, they continue that lab. But now the instructions are taken away, and we ask them, okay, you've looked at this experiment doing this, how would you go about doing a similar experiment in different conditions or in different molecules in our case? So starting to build on student-driven experiments. And the point here now is we've already given students a kind of framework. We've already said this is the setting you're in. This is the instrument you use. This is the kind of data you'll gather. This is how this works. This is how it looks. Now go off on your own. Take that first leap into building an experiment based on that kind of learning. So everything is the same apart from the kind of information the students are needed to gather. So this has worked quite well. And this is how we sort of drill that in practice. The students will do a pre-lab video aligned with the complex learning framework, where we give students generally supportive information in advance. The first session of 4, we have 4 sessions per experiment, is where students essentially complete what we would call a recipe lab. And the purpose here is really to get them familiar with the technique that they'll be doing and the kind of data that they gather and the kind of analysis protocols that they will use. They then go into the second session where they start planning out their protocol for the unknown parts. So they're given a task to do, maybe begin some initial test runs. Then they come back in for us, they come back in a week later. In the meantime, they are working on planning. And the third and fourth sessions really then are building on this investigation. But the point is, from a complex learning framework point of view, is we have given them essentially the scaffolding of this experiment. And then we are taking the scaffolding away and saying, okay, you know how all the bits work. Now try this new setting. So it's essentially everything is the same, but we're just adding on one layer of complexity. So that's really it. I think the complex learning framework is very powerful. I think it's a very useful way of considering laboratory curriculum, because it's thinking about the laboratory curriculum from the design point of view. How can we design the laboratory curriculum in a supported way where we are continually making it just iteratively more difficult for students, or continually progressing their knowledge about working and learning in the laboratory. I'll just acknowledge these people for various aspects of the work, and I will leave the slide on with complex learning framework, and I hope that there are some useful discussions. I'll be very happy to be contacted if you have any questions, and I hope you enjoy the rest of the day and the discussions.